Hello everyone, welcome to VLSI Squad. Now we are going to discuss how to calculate FIFO depth. In this video, I will tell a shortcut to calculate the depth easily. Please subscribe to VLSI Squad for more topics related to VLSI fundamentals. Now what is FIFO and why do we need FIFO? There are basically two types of FIFO, synchronous and asynchronous. Synchronous FIFOs are generally used when we need to transfer data within a same clock domain, that is sender and receiver will be working on a same clock. Asynchronous FIFO is something which is used when we require to send data from a source to the destination and both of them use a different clock. Asynchronous FIFO is used between two modules working at different clock frequencies. When there is a need to send data from one domain to other domain without any data loss, this is the important part. So why there will be a data loss? When we send data from one domain to other domain, there are high chances that data may be lost when they are working on different clocks. So what happens is when the sender sends the data, we don't know when the receiver is going to receive because their clocks are not in phase or not same. So what happens, we cannot predict when the receiver will receive the data that is sent by the sender. So there may be data loss. For this purpose we use FIFO. So FIFO is required especially when we are slow at reading and fast in writing. So when the writer is writing fast and a reader is reading slow, there may be chances that a reader can't read whatever data that is sent by the writer and there may be a data loss. Now FIFO depth can be calculated in such a way that all the data which is not read by the slower module has to be stored somewhere so that the reader can read it slowly from that FIFO. Now FIFO will only work if data comes in bursts. Like burst mean as a package, it should come as a package of data and we should not have continuous data in and out. So when the reader is slower and writing is fast, if we keep on writing continuously, reader will never able to catch up the things that are written by the writer. So if there is a continuous data flow, then the size of FIFO required should be infinite. So which is not practically possible. So this is one more thing that we should keep in our mind. So when sender sends to receiver, FIFO will help the receiver to receive the data that is sent by sender, which is coming in burst, and sender will send at a much higher rate than the receiver. And we need burst rate, burst size, frequencies, etc. to determine the appropriate size for our FIFO. So the logic, what is the main logic here? So the logic in fixing the size of FIFO is to find the number of data items which are not read by the receiver. So we can also say that FIFO depth is equals to number of data items that are left out without reading will be the size of FIFO, which should be stored inside the FIFO so that reader can read it in a later stage. And for all the examples, we are considering that module A will be the sender and module B will be our receiver. So coming about the shortcut I was talking about earlier, the shortcut formula is nothing but speed equal to distance by time that we used to do in our physics problems. So this is the triangle that for your reference you can use it, and these are the meaning of the terms I'm using. So speed in physics means that the rate of writing or the rate of reading of sender or receiver respectively. T is the time in both domains, and D is nothing but distance. Now here I'm considering distance as capacity or the size of the data which is being written or read. So let's take up the case one. So here frequency of sender module A is greater than the module B, which is receiver, and there are no ideal cycles between both read and write. So there are few other cases with ideal cycles. So in this case there are no ideal cycles. Let's consider frequency of sender is 80 megahertz and reader is 50 megahertz. Now the burst length, that is the number, the packet size we can say is 120. So 120 items of data will be coming as burst with this speed, and there are no idle cycles as I've said earlier. Now time required for one data item to be written. So that is nothing but the time period of the sender, that is 12.5 nanosecond. Now time required to write all the data. So this is a packet size, right? To write all the data, we need this much amount of time, that is 1500 nanoseconds. Now let's go towards the reader side. So at reader side, to read one data item, we need this much of time, that is time period of the reader, that is 20 nanoseconds. And for every 20 nanosecond, reader is reading one of the data item. So in the time when the burst is being given by the sender, how many data items can be read by module B is given by 1500 time by 20 nanoseconds per reading. So 75 data items the reader can read. The time that the sender can send 120 data items as a burst, reader can read only 75 of them. It fails to read 45 of the data items. So we need to save these 45 items in order for reader to complete the reading of 120 data items. So we should store these 45 data items, and that will be the size of the FIFO. So we can solve this with our shortcut formula. Question is the same. So I'll take a speed of the writer is 80 megahertz. So I'm taking it 80, and distance covered by the sender, that it has to cover 120 data items. So I'm taking distance as 120. Now time required to finish the burst. In how much time the sender can send total 120 items? That is 120 by speed of the senders, that is 120 by 80. And now let's go on to the receiver side. Receiver speed is 50 megahertz, so I'm taking it as 50. Now distance covered by the reader by the time sender sends the whole data is, distance is always speed into time. So speed is reader's speed, and time is given by the by time when sender sends all the 120 data items, and that will be calculated to 75. That means the receiver was able to receive 75 data items, and sender is sending total 120 data items. So remaining data items should be stored in our FIFO. That will be 120 minus 75, that is 45 data items need to be stored in our FIFO. So this will be the FIFO size or depth of the FIFO. Now case 2, if we take case 2, they are saying that there is one clock delay between two successive reads and writes. So one read operation that we seen earlier now will happen in two cycles, and one write cycle that happened earlier will take place in two cycles. That means in both reading and writing you have put the delay, equal delay. So their speeds will be scaled in the same quantity, and calculations will be the same. So this is just to create a sort of confusion for you. So this is same as the previous case 1. If we calculate the same as the earlier case, we'll get the same FIFO depth for this case also. So let's take with case 3. It is same as previous cases only. Frequency of writer is more than frequency of reader, which is given by 80 and 50 megahertz respectively. And burst length is same as the earlier cases. Now it is given that there are one ideal cycle between two successive writes, and there are three ideal cycles between two successive reads. What does that mean? That means that if we take reader, or if we take writer for example, the writer is writing for one clock, and then it is staying idle for one more clock to send again data in the third clock. So we can say that it is sending one data item per two clocks. So it can be understood that for every two clock cycles, one data item is written. On the similar grounds, we can understand that the reader is reading in one clock and staying idle for three clocks and then reading. That means that reader is reading once per four clock cycles. So the speed of the reader is reduced by 1 by 4, and speed of the writer is reduced by 1 by second. So time will be taken twice time. So it is 2 times the earlier time, that is 25 nanoseconds, and reading will take 4 times the earlier time. So it is 4 times the earlier time for reading one data item. In the time when writer writes all the data, how much the reader can read? So if we calculate that, we'll get 3000 by 80, that is around 37 data items are read by the reader in the time writer writes all the 120 data items. So rest of the data items are missed by the reader. So we have to store those rest of the data items, that is 83. So 83 data items should be stored in our FIFO. That will be the depth of the FIFO. Now we can discuss a shortcut method for the case 3. So that is, as I said earlier, the writing speed is reduced to half because it is taking 2 cycles instead of 1. The effective speed of the writer will be 80 by 2, that is 40, and the distance is same, 120 data items, so it is taking 120. Time required to finish the burst will be 120 by 40. So the effective speed of the reader or receiver will be by fourth of the original reader speed, so it is 50 by 4. And by the time writer writes all the data items, how many data items can the reader read will be dependent on this effective speed. So that will be 50 by 4 into, so distance is speed into time, and if we calculate that, we are getting 37 data items are read by the reader. Out of total 120 items that are written by the writer, it is only 37 data items that are read by the reader. So remaining 83 data items should be stored in our FIFO. That will be the size of the FIFO. Let's go to case 4. Here again, writer frequency is more than reader frequency, but here the catch is he is using write enable and read enable for both of the writer and reader. So this case is similar to the earlier case. There we said 1 cycle delay, and here we are saying the writer enable is only on for 50% of the time. That means the speed is reduced by half and reader speed is reduced by 1 by 4. That's what the earlier case. So they are putting the same things in different way. So this case is not different from the previous case. Case 2 and case 4 are explained just to make you understand how a same question can be asked in a different way. In case 5, now this is a different case. Now we are taking writer frequency is less than the reader frequency, and given that there are no idle cycles between any reads or writes, it is given 30 MHz is the frequency of writer, 50 MHz is the frequency of the reader, and the distance or the data items in a burst will be 120, same as the earlier case. There are no idle cycles. We already talked about FIFO is only required when writer is too fast and is sending data in bursts, and reader is slower than the writer. So here, as writer is slower than the reader can read anyhow because reader is faster. But the point is they are working on different frequencies. Here FIFO of one depth, that means only one data item to be stored, is required instead of larger FIFO. Here we may think that why we need FIFO, because the writer is slower than the reader, but we need FIFO because they are not working on same clocks, and we need FIFO to transfer data without any loss. So that is the point, as the domains are not synchronous, and we'll get meta stability if we anyhow try to send data between two clock domains which are not synchronous. So I will discuss the meta stability and clock domain crossing fundamentals in coming lectures. Let's go to next case. In case 6, we are taking that again writer is slower than reader, but here the catch is we have the idle cycles between writes and reads. We already analyzed it. So writer will take twice the normal time. It is twice the time period of the writer. Reader will take 4 times the time period of the reader, 80 nanoseconds. By the time the writer writes 120 items, how many items can the reader read? So that will be 80,000 nanoseconds. The writer can write all the 120 data items. So the reader can read 8,000 by 80, that is 100. Rest of the data items need to be stored in FIFO. So that will be the minimum depth of the FIFO. Now let's discuss it with a shortcut. So now we will take the effective speed just as in earlier case. So 30 is a normal writer speed. It is reduced to half because of the cycle delay. So 30 by 2 is 15. Distance need to be covered is 120 data items, and time required to cover this distance will be this much, and effective speed of the reader will be 1 by 4th of the actual reader speed. So if we calculate the distance by that is the number of data items that are read by module B in the time module A finishes all the burst data items, will be 100. So out of 120 data items, 100 data items are already read by the reader. So the rest of the data items, that is 20 data items, need to be stored, and that will be the minimum depth of the FIFO. In this case, reader and writer are working on same frequency, and there are no idle clocks between them. So in general, FIFO is not required if there is no phase difference. This is important. No phase difference between two clocks, and FIFO depth 1 will be required if there is some phase difference between two clocks, writer and reader. So what do you mean by phase difference? Now I have given here three clocks: clock 1, clock 2, clock 3, and clock 1 and clock 2 are of same frequency, and both of them are starting and falling at the same time. So clock 1 and clock 2 will be in phase, and there is no need of FIFO if they are using these clocks for writer and reader. But if you take clock 1 and clock 3, they are of same frequency, but clock 1 is starting here, clock 3 is starting somewhere here. They are not starting at the same time and not falling at the same time. This is what I mean by phase difference. If there is phase difference, when we send data from sender, that is clock 1, we don't know when this receiver is reading, so there may be data loss. So for that, we need a FIFO of size 1 in order to avoid any possible data loss. And this is the next case. Again, frequency of writer and reader are same, but here we are taking the idle cycles. Again, time required for the writer to write one data item will be twice the actual time, that is 40 nanoseconds. The reader will read in the time of 4 times of the actual time, is 80 nanoseconds. In 4800 nanoseconds, the writer will write 120 data items. In meantime, the reader can read 60 data items. So rest of the data items, that is 120 minus 60 data items need to be stored. So that will be the minimum size of the FIFO. So if we do this with our shortcut, the effective speed of the sender will be half. Distance need to be covered is 120. Time to send is all 120 data items will be distance by speed, that is 120 by 80. And effective speed of the receiver, or maybe module B, is 1 by 4th of the speed of the receiver because of the idle cycle. So that will be 50 by 4. Now distance covered by the reader by the time writer travels or covers this much distance of 120 data items will be speed into time. So we'll get 60. By the time writer writes 120 data items, reader was able to reach 60 data items. So rest of the 60 data items needs to be stored in the FIFO. So that will be the minimum depth or size of the FIFO. So this is a special case. We are saying that writer will write 80 data items per 100 clock, randomization of 20 data items. That means writer can write any way. It is possible in any way, any random way. You can say like this, in any random way it is possible, but we have to take the worst possible scenario. I'll explain you what is worst possible scenario also. So outgoing data means reading data will be going at a rate of 8 data items per 10 clocks. Given burst size is 160. What do they mean? The given specifications are like data items per clock, so they are showing the writing and reading frequencies, but we have to see what is the worst case scenario. So worst case scenario is when the writer keep on writes the data, that is how much the writer can send data continuously. That is the worst case scenario. The worst case scenario is in which the writer has to send maximum number of data items in a given time. Let's take various scenarios. Here you can take case 1. So it is sending 80 data items and it is remaining idle for 100, remaining idle till 120, and again sending data. So here we have some idle time for reader to read. So this is not a worst case scenario. Even here we have idle case between two writing. So this is not a worst case. Even here we have idle time between two writes. So this is not a worst case scenario. And if we take randomly also, this idle time will give reader some time to read. So we have to take this case. Here there are no idle gaps between two writes, so we are taking the longest write without, like, this will be the worst case scenario. So we have to take the longest write without any delay. So it may remain idle for first 20 cycles and keep on write till 100, and then immediately start writing at 100, and then till 180 keep on writing. So that means this 160 data items are sent in a one go. So this will be the worst case scenario. In between there is no time for reader to catch up or read any data. So we are taking this is our worst case scenario, and let's solve the case 9. Here we are taking 160 clock cycles for 160 data items is the speed of the sender module. So that is a worst case scenario. The reader speed will be 8 data items for 10 clock cycles, it is given. In the time when sender sends 160 data items, how much data items can reader read? So it is sending 160 data items per 160 clock cycles. So 160 clock cycles into 8 by 10 is the speed of the reader. So that is 128 data items. Out of 160 data items, 128 data items have been read. So 32 data items are left out without reading by the reader. So this should be the size of the FIFO. So 32 will be the minimum size of the FIFO. So if we solve it by our shortcut method, what is the worst case scenario? Worst case scenario is fastest write and slowest read. So fastest write is nothing but 160 by 160 instead of 160 by 200. It is 160 by 160 is the fastest rate. That is a maximum possible fastest rate that we can get from a writer's side. So that is 160 is the time required for writer to write 160 data items. Speed of the receiver is given as 8 by 10. So distance covered by the receiver by the time sender sends 160 data items will be distance is speed into time again 8 by 10 into 160, that is 128 data items. So 128 data items are successfully read by the receiver by the time sender sends 160 data items. So what are the remaining 32 data items? So these should be stored in a FIFO, that will be the minimum size of the FIFO. So this case is a different. So here specifications are given in a very different way, and we need to understand these specifications, and that is very important to solve this problem. We need to make sure that FIFO should not overflow or underflow. These are the three given equations. They didn't specify anything explicitly. So now let's assume some numerical values to solve this problem. Let's assume frequency of clock B, that is reader frequency, as 100 MHz. According to this equation, the frequency of clock A, that is writer frequency, will be 1 by 4th of the reader frequency, that is 100 MHz by 4, that is 25 MHz. He also given the burst length indirectly. From the second equation, we can understand that burst length is 100. So 100 data items is a burst length. So this is given indirectly, and we have to understand this. Now time required to write one data item will be time period of the writer. So that is 1 by 20 megahertz, that is 40 nanoseconds. And time required to write all the 100 data items will be 4000 nanoseconds. But according to equation 3, only 25% of the time the reader is reading. That means out of 4000 nanoseconds, only 25% of the time, that is 1000 nanoseconds only, the reader is reading the data, and rest of the time the reader is not reading the data. So we have to calculate how many data items are written in the time when reader is not reading the data. Those data items are 3000 nanoseconds is not reading, and time required to write one data item is 40 nanoseconds, that is 75 data items the reader is not reading by the time reader is staying idle in that 75% of the time. That means these 75 items are yet to be read by the reader. So this will be the size of the FIFO. So this is a big tricky question. Solve it again in order to get more clarification. So thank you very much guys for listening to this lecture. Please subscribe to VLSI Squad to learn more VLSI fundamentals. Comment what do you want to learn in the next lectures.